In all the examples that we've looked at thus far with finding the area between two curves, we've always done the integral with respect to x. In other words, we took top function minus bottom function, right? We went up and down. But you guys can clearly see in this example that we have right here, where we're going to try to compute the area bound by these two functions, that there's a split. So right here, it starts out with a function y equals square root of 2x, but then it has this linear function, all right? So the heights are completely different functions once it hits this point, x equals 2, all right? So now I want to illustrate two different ways to be able to evaluate this integral. And you're going to see that if we try to do this with respect to y, it's a lot easier, okay? But first of all, let's just set up two integrals to represent the area in terms of x, right? So for area 1, clearly we can see 0 to 2 are the bounds. And the top function is the square root of 2x, and the bottom function is just y equal 0. All right, so really we don't subtract out anything. I mean, technically it would be square root of 2x minus 0, but we don't even care about that. So this would be integral square root 2x dx, and that would represent area 1. And let's go ahead and compute that. Then we'll go ahead and worry about area 2. To compute this, what we're going to do is we're going to split this up. So we're going to have the square root of 2, 0 to 2, square root of x dx. Okay, so I just factored out the square root of 2. And we know that the square root of x should be written as x to the 1/2, so that way we can integrate. Square root of 2 times, when we add 1 to 1/2, we get 3/2, and then we divide by 3/2 from 0 to 2, right? And so when we substitute, this is going to turn into the square root of 2 times 2/3 times 2 to the 3/2. And if we substitute 0 back in, we're just going to get 0 to the 3/2, which is 0. All right, so technically it'll be minus 0. All right, now check this out. When we simplify this, we could certainly use a calculator, but we know that the square root of 2 is really 2 to the 1/2. And notice that we have a 2 and a 2 right here being multiplied. It's all multiplication. So we would just add these two values together. And so this would actually be 2/3 times 2 to the 1/2 plus 3/2, which would be 4/2, which is 2. So ultimately, this would wind up being 8/3. Now remember, that's just for area 1. We still have to compute area 2. To compute area 2, first of all, we need to get this expression or this equation in terms of y. Okay, so this is A2. So we have x plus 2y equals 6. If we solve that for y, y is going to be equal to 3 minus 1/2 x. All right, so what I did was I just subtracted x, divided by 2 with everything, and that's how I got to this expression. Notice that the bounds are going to go from 2 to 6 on the x-axis. And so the integral for this is going to be the integral from 2 to 6 of 3 minus 1/2 x dx. All right, a little bit tougher to evaluate because now we have two non-zero bounds. Not too hard though. 3x minus 1/4 x squared from 2 to 6. Substituting 6, we get 3 times 6 minus 1/4 of 6 squared minus 3 times 2 minus 1/4 of 2 squared. All right, and you can see this turns into something fairly nice. So we get 18 minus 9, so this will be 36/4, minus 6 plus 1, right? Ultimately, I believe that this is going to turn into 5, because this will be 9. 9 minus 6 is 3. It's 4. Okay. Now, don't forget, though, that we already had area 1, which was 8/3. So A1 plus A2 is going to be 8/3 plus 4, which is 8/3 plus 12/3, or 20/3. All right, so Pretty nasty process to get to that. All right. And this, by the way, this was a pretty simplistic one because we really didn't have that difficult of functions to work with. Now, let's see what would happen if we change this to be able to evaluate this integral or this area in terms of y, right? Now, remember that we had y equals the square root of 2x. If we solve that for y, or I'm sorry, for x, that would mean that y squared equals 2x, or 1/2 y squared equals x. So that's how so basically what we want to do is we want to solve each of the given functions in terms of y to get a function x equals something in terms of y. Remember we had x plus 2y equals 6. If we solve that for x, this one's pretty easy. X equals 6 minus 2y. Whenever we try to integrate with respect to y, what we're going to do is we're going to go from left to right, and we're going to add up all the rectangles. So there's a rectangle here, there's a rectangle here, and notice they're of varying lengths, if you would. All right. And so y is going to start at 0, and it's going to go all the way up here to the point 2, 2. All right. So we know that y is going to be equal to 2 at that point. And we're moving from left to right, right? So whenever we figure these sorts of integrals in terms of y out, we're moving from left to right. And so our integral, the left function is going to be this x equals 1/2 y squared. The right function is going to be 6 minus 2y. And so here's our integral. Integral, lower bound 0, upper bound 2. The right integral, which is the quote unquote top function, is 6 minus 2y. The bottom function, or the lower function, is going to be 1/2 y squared. All right. Now, I want you to notice that this integral is actually a little bit easier to evaluate. Reason being is because now we don't necessarily have to worry about too much about the different first of all, the lower bound is 0, but secondly, we don't have two integrals to evaluate. Right? So evaluating 6y minus y squared, all right, minus 1/6 y cubed from 0 to 2. Now, when we substitute back in, we get 6 times 2 minus 2 squared minus 1/6 times 2 cubed minus 0. This is going to be 12 minus 4, which is 8. This becomes, it's going to end up being 8 over 6. All right. If we get a common denominator this time of 6, excuse me, that's going to end up being 48 eighths, or 48 6, excuse me, minus 8/6, which is going to be equal to 40 over 6, which is 20 over 3. All right. And I'm hoping that's the same thing we got up here, which it is. All right. Now notice that this was literally 1, 2, 3, 4, 5, maybe 6 lines. All right. A pretty easy computations. Up here, I mean, 1, 2, 3, 4, 5. Just for the first one, 6, 7, and we had to solve 8, 9, 10, 11, 12. So it was almost double work, okay, if you want to count these as a couple lines. But regardless, it was still easier for us to be able to evaluate this area in terms of y. And that's the charm of doing this, is that if you could recognize that you have a fairly nice integral in terms of y, then it makes it easier. It's not always impossible to evaluate in terms of x, but sometimes it's just easier. So we'll look at one more example to where we have a function in terms of y instead of x to be able to evaluate these sorts of areas.